Well, welcome everybody to the 450-131 Probability of Failure workshop. My name is Adam Mullins, and I am currently the ASA 210 Flight Safety Analysis Branch Manager on detail, filling in for Sean, while Sean is currently on detail with ASA 220 in our System Safety Branch. Today, we're going to talk about probability of failure, as described in 450-131. I'll also note that recently, just over the last week, AC 450-131 was recently released for public comment and published to the Federal Register. So that is available to you all. I encourage you to take a look at that and provide FAA with feedback on that AC as you read through it. So this workshop will focus on that AC. There will be a lot of references to that AC. I realize that it was recently released, so you may or may not have had a chance to take a look at that, but that is our focus today. I'm your host today, but I'm not your subject matter expert. So with that, I will introduce Ms. Christine Zinsi. Chrissy is a long-standing member of the Flight Safety Analysis Branch in the Office of Commercial Space Transportation. She's one of our probability of failure subject matter experts, and she's also the chair of the Common Standards Working Group Probability of Failure subgroup. And with that, Chrissy, I will turn it over to you to get started on the workshop.
Thanks, Adam. Can you hear me okay?
Yep, gotcha.
Great. Well, welcome everyone. Like Adam mentioned, I'm a flight safety analyst with AST, and I'll be going over the probability of failure workshop. I have a couple of stops in here for questions, might add one or two more stops depending on how fast we get through these. So we'll take questions at those times. Okay, next slide, please. Okay, the purpose of a probability of failure analysis is to characterize the likelihood of hazard-generating events that could constitute a threat to people or property. So this workshop provides explanation and guidance on the 450-131 probability of failure analysis requirements. I'll also discuss how 450.115C applies to 450-131 and how it should be addressed in the application. I'll also provide an overview of the probability of failure advisory circular that Adam mentioned, and I'll go over an example means of compliance. Just as a reminder, this is a guidance document. Its content is not legally binding in its own right and will not be relied upon by the department as a separate basis for affirmative enforcement action or other administrative penalty. Conformity with the guidance document is voluntary only. Nonconformity will not affect rights and obligations under existing statutes and regulations. Next slide, please. Okay, so for this first section of the slides, I'm going to go over an explanation of each part of the 450-131 requirements. So 450-131A is a general overview of 131, and it states for each hazard and phase of flight, a flight safety analysis for a launch or reentry must account for vehicle failure probability. The probability of failure must be consistent for all hazards and phases of flight. So before I get into this, the way the AC is laid out and the way these slides are laid out, we go into detail on specific phrases used in the AC so that you all get a better understanding of the intent of the requirement. So for example, 450-131A uses the phrase vehicle failure probability. This is the likelihood that a launch or reentry vehicle has a failure during flight. When we say for each hazard in the requirement, for each hazard means debris risk analysis, far field overpressure blast effects analysis, and toxic hazards. Excuse me. And then it also says for each phase of flight, the failure probability must be accounted for. So a phase of flight is a period of flight between two milestones in the vehicle flight sequence, or the probability of failure distribution for each reasonably foreseeable failure mode is homogeneous. A phase of flight can be discrete, such as stage separation, or it can be continuous, such as a stage burn. All phases of flight should account for the full time span of flight within the scope of the flight safety analysis. So the reference here is for the scope of the flight safety analysis is 450.113. So 451.13 describes the scope for a suborbital launch, an orbital launch, a disposal, and a reentry. An operator should strike a balance between the number of phases and the availability of data for each of the given phases. So we'll go into, applicable data depending on number of flights of your subject vehicle. But just a note up front here that, the more phases and events you have, the higher fidelity, it may mean that less data is available per phase or event. So that's just something to keep in mind. Um, Consistent for all hazards and phases of flight. So consistent here means in agreement. It doesn't necessarily mean that the operator can't can't vary the probability of failure within a defined uncertainty for the same event in different contexts. For example, the probability of failure for stage 1 versus stage 2 could be varied within a given uncertainty at different sites, depending on perhaps the overflight during stage 1 or stage 2, and which would give you the more conservative collective risk. Debris or toxic analysis, it can be varied within those analyses. And this is in order to be conservative to meet 450.101G. And this is actually taken from the Part 450 preamble, and again, it's described in more detail in the advisory circular. Next slide, please. Okay, so 450.131A describes the requirements for a vehicle or vehicle stage with fewer than 2 flights. And it states, for a vehicle with fewer than 2 flights, the failure probability estimate must account for the outcome of all previous flights of vehicles developed and launched or re-entered in similar circumstances. So the first thing to note here is the probability of failure requirement treats probability of failure analyses differently for the first 2 flights of a subject vehicle, differently than flights after that. Historical data shows that experience makes a significant difference in failure likelihood. One second, please. So how do you determine, can you go back? Sorry. So how do you determine what constitutes a vehicle or vehicle stage in this context? So significant upgrades or configuration changes to a subject vehicle may make past flight history inapplicable or less relevant. And by less relevant, I mean weighted less if you're using a weighting methodology. So for example, significant upgrades or configuration changes, those can include an entirely new or upgraded stage, a new vehicle developer, if a vehicle is built up of stages and guidance systems on previous vehicle versions, but not as an integrated vehicle. So those are some examples of significant enough upgrades to make past history inapplicable or given less weight. So the requirement states that the probability of failure must account for the outcome of all previous flights of vehicles developed and launched or re-entered in similar circumstances. So accounting for the outcome here means scoring of the flight history of the historical data. And scoring means counting a success or failure or no score of the phase or event. And then if there is a failure, what the failure mode is. And then developed and launched or re-entered in similar circumstances. So for a vehicle with fewer than 2 flights, an operator should use historical data of previous flights to account for the influence of how the vehicle is developed and operated on the true probability of failure. To define the historical data set, an operator should define similarity criteria and then determine if that criteria is meaningful, which I'll talk about in the next few slides. And then a note here, each phase of flight of the subject vehicle may have different sets of historical data, depending on data availability and what your criteria is. Okay, next slide, please. Okay, so the AC goes into a lot more on scoring. Some cases are given here with examples. I won't read through each example, but just to give an overview of the cases, if a single failure occurs during concurrent events, the failure should only be scored for the relevant event, and then other concurrent events would receive no score. If two independent failures occur, whether the events are concurrent or non-concurrent, then both events should be scored as a full failure. If a phase does not begin due to an earlier phase, that phase should receive no score. So I'll go over the example here. If the vehicle is lost due to an explosion shortly after takeoff during stage one burn, then the stage one burn should be scored as a failure, and all phases after that would receive no score because no observation took place during those phases. The advisory circular does allow for the possibility of partial failures, and partial failures may be scored in multiple phases to account for the influence of a failure on the probability of failure estimate if the failure had the potential to occur in a different phase. When scoring partial failures, the scoring should also include the number of observations of that phase. And then we give some guidelines on when a partial success should be used and when zero success should be used. So a partial success should be scored if the vehicle successfully completed the phase, and zero success should be scored if the vehicle did not successfully complete the phase. And I'll give everyone a minute to take a look at the examples.
Excuse me, Chrissy.
Yes,
Could a partial failure also mean loss of redundancy?
loss of redundancy.
In the FSS
Um,
designs, we have a lot of redundant components. So if we lose the A leg, but the B leg is still working, would that be considered a partial failure or a full failure?
I think if there is the potential to lose the vehicle, then yes, it's possible it could be scored as a partial failure. I won't say definitely. I think it depends on the circumstances. Not sure if anyone else has any thoughts on that.
Hey,
Sure, yes.
Chrissy.
It is possible that anomaly, so not the in a later part of the
Yep.
AC and the regulation, it talks about anomalies. So anomalies are things that are not didn't actually cause a failure. Scoring anomalies is a very tricky topic, but they sometimes do result in partial failures. Generally, the case where if under different circumstances, the same failure the same anomaly could have produced a failure, then that should be considered a failure. But we don't want necessarily to count, um, you know, partial failure as a lack a drop in redundancy as a failure because the vehicle is built with redundancy in order to protect against that. And we want to encourage better redundancy in system. And from a safety perspective, more redundancy is a good thing. So in general, it does get tricky. And likewise, we don't want to penalize operators who are doing a better job of capturing what anomalies have occurred. In fact, that tends to produce a higher reliability in the long run if anomalies are actually observed and then dealt with appropriately. That's better for future reliability.
Thank you.
Thanks, Eric. It's a good explanation. Okay, I think we can move on to the next slide. So when you are determining the historical data to use to develop your probability of failure in order to meet 131A1, there are many different criteria you can consider. And we listed some in the AC that have had major influence. And we grouped those into three categories: vehicle characteristics, a reliability approach, and organizational processes. So vehicle characteristics, you would consider similarity as it relates to vehicle configuration, vehicle history, and technological maturity. For similarity of reliability approach, you could consider whether an operator was using a fail fast, fail forward approach, if they were applying some sort of standards such as NASA human spaceflight standards. You could consider payload value, factors of safety, things like that, to determine how similar the subject vehicle is to um, vehicles launched or re-entered in similar circumstances. And then lastly, organizational processes is also important to consider. So this would involve how similar the system safety program maturity is. And this can be evidenced by procurement information or requirements imposed by customers, regulations, launch sites, et cetera. And then also developer experience. And one of those I'll talk about in the next slide. But for example, we've seen that brand new developers with no experience and who are using a brand new rocket engine demonstrate statistically significant higher failure probabilities than others. Next slide, please. So an operator may determine if criteria is meaningful through a Bayesian uncertainty analysis. This is one option of showing that criteria is meaningful. The advisory circular goes through more detail on this example with equations worked out to give you better understanding. But a high-level overview is shown here. The figure shows the probability of failure distribution for the first two flights of new vehicles by new operators. That's abbreviated by NN, and those vehicles are shown in blue. And then NN was further categorized into high, medium, and low newness, I'll call it, using a beta distribution. And that high newness, high NN, is in green, and that's what I described on the previous slide. Those are vehicles with no developer experience and a brand new rocket engine. And you'll see there that the high newness in green has very little overlap with other groups, demonstrating statistically distinct results. So a reasonable conclusion from this analysis is that the NN could be further decomposed into two groupings, one that combines medium and low, and one for high. So this is just an example of how you could determine if your criteria is meaningful. Next slide, please. Okay, so the next part of the requirement is 131A2, and this applies to a vehicle or vehicle stage with two or more flights. So for a vehicle or vehicle stage with two or more flights, the vehicle failure probability estimates must account for the outcomes of all previous flights of the vehicle or vehicle stage in a statistically valid manner. The outcomes of all previous flights of the vehicle or vehicle stage must account for data on any mishap or anomaly. So this is basically saying an operator must account for subject vehicle history if it has two or more flights of the subject vehicle. In most cases, historical data of similar vehicles should continue to be accounted for as well. The AC goes into some specific cases where perhaps similar vehicles can be deweighted, but in most cases, it's statistically valid to continue to include those similar vehicles from 131A1. Again, accounting for the outcome means scoring. In this case, it means scoring of the subject vehicle, and that should be provided in the appropriate mishap or post-flight report. Statistically valid manner. So this is discussed more in AC 450-115-2, but I will talk about specifically how it applies to probability of failure analyses on the next slide. Mishap and anomaly are both defined in 401.7, so I brought those definitions here. So for mishap as defined in 401.7 has a number of criteria that's considered a mishap, but we listed here the mishaps that should always be considered failures. Those are unplanned permanent loss of a launch or reentry vehicle during licensed or permitted activity, the impact of hazardous debris outside of the planned landing site or hazard area, and then failure to complete a launch or reentry as planned. There's a number of other criteria, I'll call it, that's considered a mishap, and those may be considered failures depending on the circumstances, but we listed here what should be considered failures. Anomaly is a condition that deviates from what is standard, normal, or expected. Eric touched on this, so these should be identified in the post-flight data review per 450-103-D3. And then an operator should define criteria within their probability of failure analysis methodology to the criteria that should be used to determine what type of anomaly is considered a failure, or what level of anomaly is considered a failure. Next slide, please. Okay, so this is a little more on statistically valid manner. So an operator should have criteria that they should use as the checkpoint for the probability of failure method reevaluation. So basically, after a failure, an operator should have some kind of check to determine that their probability of failure method is still valid, or if it needs major or minor updates. This helps to continue ensuring compliance with 450-101G. That states that the method must produce results consistent with or more conservative than the results available from previous mishaps. We did provide an equation that an operator may use as this checkpoint, and that's shown on the slide here. The inputs are the difference between flight ordinals of the two most recent failures, and then the conditional probability of failure predicted for the most recent failure. If the equation above holds true, the operator should then consider whether method updates are warranted. And on purpose, we're not prescriptive about this, what warrants a method update, whether that's redefining similar circumstances, adjusting weighting factors, adjusting allocations, or perhaps the circumstances warrant no method update is needed with justification provided. This is just to be used as a checkpoint. Okay, next slide.
So there was a question before we move on. There's
Oh.
also a question in the chat from Matt Georges. Are further productions of the same vehicle with the same production method considered new vehicles? Well, I would say that is not a sufficient criteria to determine whether or not a vehicle is new. Design, obviously, the similarity of design between a vehicle and a derivative or another one is the key thing. So yes, there's not a firm line because we know vehicles are evolving with time, but the AC has some examples, that draft AC, of what does constitute a new vehicle versus a one that's still the same vehicle. So I would check the AC. There's more there, but same production methods is not a sufficient standard.
Okay, thanks, Eric. Okay, so 450-131B provides a definition of failure for use in the probability of failure analysis. For flight safety analysis purposes, a failure occurs when a vehicle does not complete any phase of normal flight, or when any anomalous condition exhibits the potential for a stage or its debris to impact the Earth or re-enter the atmosphere outside the normal trajectory envelope during the mission or any future mission of similar capability. So the definition of failure here should be used to determine the outcomes of previous flights of either the subject vehicle or the vehicles developed and launched or re-entered in similar circumstances. And also noted the outcomes of previous flights of the subject vehicle must account for data on any mishap and anomaly. So that's also where the definition of failure comes into play. So we break down the definition of failure a little more here. A failure has occurred when a vehicle does not complete any phase of normal flight, a vehicle stage or its debris travels outside of the normal trajectory envelope, a vehicle stage or its debris impacts land or water outside of planned impact regions, an anomalous condition produces unexpected and potentially hazardous debris, an anomalous condition exhibits the potential for the vehicle to fail in any of the ways described above during the mission or any future mission of similar vehicle capability. Next slide, please. Okay, so just to continue breaking this down, so what does it mean when a vehicle does not complete any phase of normal flight? The probability of failure method should define how the failure will fit within the defined phases and events. And so the draft AC goes into a lot of examples here. I'll go over the kind of a high level here. But yes, if you're interested in more, I definitely recommend checking out the draft AC. And we can try and answer any questions here as well. So this is an easy one. If the failure initiation and failure manifestation occur in the same phase, then it should be scored in that phase. If the failure initiates in a phase but does not manifest until a later phase, then the operator needs to consider the specific circumstances of the failure and available information, including malfunction trajectory simulations that will capture the failure. So an example given here, a propellant leak develops in an upper stage during first stage flight. There is no effect on the first stage flight. This failure should be counted when the failure manifests, which may be in the upper stage ignition event if it's ignition that fails, or during the burn phase if the propellant runs out. So as you can see, it's really depending on the circumstances and how the malfunction trajectory simulations capture the failure. And again, more examples are provided in the draft AC. So exhibits the potential. This accounts for situations where no hazard to the public occurred, but it would likely have occurred if the same anomaly, but it likely would have if the same anomaly occurred on another operation of the same vehicle. For instance, on a slightly different azimuth or with a heavier payload or at a different time in flight, etc. For a stage or its debris to impact the Earth or re-enter the atmosphere. This means if a stage or its debris shows evidence of or exhibits the potential to travel outside of the normal trajectory envelope or impact outside of a planned impact region, even if it demises upon reentry, then a failure has occurred. Next slide, please. So what does outside of the normal trajectory envelope mean? The intent of this, the meaning described in the AC is a deviation in present position, instantaneous impact point, and or time outside of the set of incertitude trajectories required by 450.117A2. Whether you're outside the normal trajectory envelope or inside should be assessed at the beginning and end of each phase of flight. And to assess this, an operator may use a factor of 2 of the 97% confidence of the three-dimensional spatial volume and time distribution. So I discussed this a little on the last slide, but during the mission or any future mission of similar vehicle capability, here an operator should consider if the anomalous condition exhibits the potential for the vehicle to fail during launch or reentry itself, or at a later mission with similar objectives. So an example given here is an orbital launch vehicle substantially underperforms outside of the normal trajectory envelope during a mission, but still reaches its intended orbit because the payload is lighter than the maximum payload weight. This anomaly should be counted as a failure in this case, since the vehicle went outside of the normal trajectory envelope, and a future mission with a heavier payload or targeting a different orbit has the potential to not achieve orbit and impact the Earth outside of hazard areas. Are there any questions we want to go over?
Yes, we have a couple questions in the chat. So the first question is the FAA willing to accept the Christmas tree method used in 417 to determine probability of failure for Flight 3 and beyond?
So this one, the FAA is working that question. So I think we will get back to you at an FAA office hours on that one. It's something that we're tracking that as a question. I know it's come up in previous office hours. I think the short answer is in certain cases, yes. But we'll get back to you on more specifics with that.
Yeah, that's the answer I was going to give, Chrissy. Thanks.
Great.
Okay, second question. If a vehicle is designed to be able to withstand a number of premature engine shutdowns, in other words, engine out failures, does a premature engine shutdown still count as a failure? So you're robust to engine out cases, you experience an engine out. Does that need to be counted as a failure or a partial failure?
Well, sure, I'll take this one. So this is one that you need to incorporate that in your normal trajectory analysis. If that is a planned situation, then it needs to be counted as a normal trajectory. And if it's a normal trajectory, then no, it's not a failure. As you will see in the draft AC, it talks about that's a key criteria for whether something's a failure is if it remains within its normal trajectory envelope.
All right, thanks, Dr. Larson. Another question for the nominal envelope, is incertitude here meaning variability and incertitude, or in other words, uncertainty? I don't know, Dr. Larson, if you want to take that one as well.
Eric, correct me if I'm wrong. It's just incertitude, uncertainty, not variability.
So that would be for the basically variability means that's your intended. The variability goes away when you actually make your launch commit decision. So is it within the uncertainty of your flight, of that intended flight?
Is this the pause point for questions on any of the material thus far?
Sure, we can take more questions.
Okay. Going back to phases of flight, the slide mentioned continuous phases as a type of phase, and in the AC it says that continuous phases shouldn't contain any key flight safety events, but in past guidance material it has said you should not contain more than one key flight safety event. So it's a slight change, and I was wondering if you could expand on why that change was made.
It should match other ACs, so that may be a good comment to submit to the public comment period. It should match the other AC, so that's a good catch.
Okay, yeah, I was really struggling to think how I would get some of my continuous phases to not have any flight safety events.
Okay.
When you were talking about adjusting the POF up and down within the uncertainty bounds, you just kind of said, hey, you could adjust it up if there's a phase that drives more collective risk and down in a phase that drives another. Were you talking about producing several different probability of failure analysis results, specifically targeting different types of risk, or is this just one probability of failure analysis result set, but targeting what we think is on the whole the most conservative?
That's a good question. I think it would depend. I think if it's obvious, you would only need to demonstrate the one answer, but otherwise the sensitivity analysis might be appropriate.
Yeah, because thinking about your example for Vandenberg, where the stage one drives higher collective risk, so you up the stage one and decrease the stage two, but then that's going to produce a shorter NOTAM for your stage two.
Mhm.
So is that okay because the collective risk is higher, or do I need a separate POF to now produce the longer NOTAM as well?
Um, that one we might have to, that might be a certain circumstances that we'd have to discuss with the applicant, uh, unless anyone has any other thoughts on that one.
Okay, that's no
Yep.
problem. It's very hard
Okay.
to say like this is the one conservative set, right?
Yes, that's very true.
One thing that I was surprised to see missing from the similarity criteria was flight ordinal. Traditionally, like first and second flights have been considered a similarity criteria, and so you would only go and find the flight history of other first and second flights. Is flight ordinal still considered a similarity criteria? And if so, where would it fit in the kind of categories that you guys presented?
Adam, could you go back to the categories? Yep, there it is.
Yeah, so that's part of vehicle history.
Yes, vehicle history. Yep.
The draft JC is not clear on that. Then can you, a comment would be great.
Yeah, okay. Yeah, that's very helpful to know. And then the other thing that I struggled with on the similarity criteria was obviously when you're building this flight history database, you tend to get a lot of international vehicles in there. And other than the payload value, I couldn't find many of the listed factors for reliability approach or organizational process for international vehicles. I was wondering if you had any tips on how to approach that.
So I would say that if I were doing it, I would say there's probably less weighting given to those. There's more uncertainty in the similarity. So this is where a similar or not a binary gets very challenging to put because yeah, if you don't know, they are somewhat similar, but there's more uncertainty in that similarity. So that would result in a lower weighting factor. That I think that's yeah, that could also be something that we could think about. Probably, if you want to submit that as a comment, it's probably something for a future AC. We do have plans to expand which the MOCs that are in this. We wanted to get one that was very clear that we could put out there, but this is an area for consideration for a future MOC.
Okay, yeah. I mean, the lists were helpful, and I could see how I could develop some of those things for US vehicles, but for Russia and China or other countries, I'm not sure how I would get some of those things.
Yeah, I understand, and it gets more challenging to try to figure out, well, how relevant is that flight history from the other countries to what we're doing? And that is there's definitely more uncertainty in how relevant it is.
Yeah, that makes sense. Okay, this is a big one that has always been unclear. Going from 131A1 to 131A2, when I am doing the POF analysis for my second flight, so I've not yet had two flights, how do I use the first flight's outcome? Or do I not use it at all because I'm not in my second flight yet?
So we have interpreted A1 and A2 as minimum requirements. And generally, it is a good idea to use both. That is allowed by the requirements to yes, use the first flight outcome when looking at second flight as well.
So is it generally a good idea, but it's not required or it is required?
I think, I mean, I think we'd have to, I think it would, this is, again,
So-
depending, yeah, go
so-
ahead.
My take is that that is not something that's easy to definitively say because it depends very much on the operator's method. I mean, I think if the operator is proposing some sort of Bayesian method, it's easy to interpret A1 as development of your prior, and it's kind of easy to interpret A2 as updating that prior. So the statistically valid thing to do for such a method would be to include your outcome. And we can't definitively say that because there could be non-Bayesian methods or other things that might not be the same for. Over.
Copy. Thanks, Sean. Yeah, that's helpful. That actually goes into another part that I would love to see in the AC and that has been included in past guidance material is once you have your flight history and it's all scored, you have your successes and failures, what method do you use to actually produce your conditional POF estimate? I didn't find that anywhere in the AC. I saw a sentence saying a Bayesian update approach is a common approach, but in previous guidance, that Bayesian update approach has been kind of listed out and shown, and here you kind of just jump from you have your scored database, and then you jump straight into using that conditional probability result. So that's just something I would like to see added.
Yeah, I think that goes into what Eric was saying about we would like to add additional means of compliance for different vehicle types. So that's the plan in the future. But yeah, noted.
So I want to be considerate of our time here. We do have a couple of questions in the chat that I think we can knock out two in one. So these two questions are related to failures on the ground prior to flight. Should a failure on the ground prior to flight that causes a vehicle failure be scored? For example, a stage 0 failure that causes an engine out at the start of a launch, resulting in a failure to achieve a planned mission, or just in general, an anomaly prior to flight that results in some sort of no-go or scrub. Should those be considered in the flight probability of failure assessment?
So this, I think we will talk about in future slides. It's 131C, and it defines previous flight and when that starts.
Okay, and then last question. Common upgrade to launch vehicle is stretching the tanks to add performance. Is that going to change the probability of failure? Not sure if the upgrade is significant enough. So maybe in general, how do we assess launch vehicle modifications with respect to probability of failure?
So yes, we didn't give a black and white number on this. I think that would be up to the operator or applicant to propose if basically if it's going to be weighted the same or differently. But yeah, that would be up to the applicant's method to propose that.
Okay, I think we're ready to keep going, Chrissy.
Okay, thanks.
Sorry.
I think next slide. Yes.
Great.
Okay, yes. So previous flight is defined in 450.131C. So for flight safety analysis purposes, the flight of a launch vehicle begins at a time in which a launch vehicle lifts off from the surface of the Earth. And then a flight of a reentry vehicle or deorbiting upper stage begins at a time in which a vehicle attempts to initiate a reentry. So this goes back to a few of the questions we got. So this definition should be used to determine applicable flights of the subject vehicle or those historical vehicles that are developed and launched or re-entered in similar circumstances. So this may include amateur rockets, permitted activity, U.S. government launches, foreign launches, etc., or re-entries. So what does liftoff from the surface of the Earth mean? So this occurs when a vehicle moves relative to the launch platform, whether that's land or water. This does include captive carry unless the demonstrated reliability exception applies for 113B. A deorbiting upper stage is a stage that returns or attempts to return from orbit to Earth in a controlled manner, including disposal. And then the time in which a vehicle attempts to initiate reentry is, we define this as the time at which reentry flight begins, a scope of license per 450.3C. And this does include random reentry since it exhibits the potential for the stage or its debris to impact the Earth. This is something we've had a lot of discussion on and would definitely be looking for feedback and comments on time in which a vehicle attempts to initiate reentry in the draft AC. So if you have thoughts on that, definitely be interested. Next slide, please. So 131D describes allocation requirements. So the vehicle failure probability estimate must be distributed across flight phases and failure modes. The distribution must be consistent with, and the requirement goes on to describe basically subject vehicle data and historical data, which I'll go into more detail in a few slides. But first, distributed across flight phases. So this means that the probability of failure should be allocated across all phases of flight within the flight safety analysis scope per 113A, and then distributed across failure modes. The probability of failure should be allocated across failure modes or failure response modes applicable to the subject vehicle. So I'll talk more about failure modes versus failure response modes in the next couple slides. And then again, consistent means in agreement with. So the method can directly use historical and subject vehicle data using Bayesian inference, for instance, to account for uncertainty. However, the methods don't need to directly use that data as long as the results are consistent with or more conservative than methods that directly use the data. So an example here is going to be given in the example means of compliance at the end of these slides. Next slide, please. So first we'll go into failure modes. So a failure mode is a unique combination of three elements: the initiating subsystem or system of the failure, the resulting manifestation of the failure, and the flight event where the failure occurs. So failure modes are used to classify historical failures and should be linked to the subject vehicle's functional hazard analysis. So there are some examples of failure modes here. A propulsion system failure, turbopump failure of the only engine leading to a total loss of thrust during stage 2 burn, a guidance system failure leading to total loss of thrust during stage 2 burn, a propulsion system failure leading to no thrust during initiation of stage 2, and a flight safety system failure, such as a data to the MIFCO screen lost leading to a loss of thrust during stage 2 burn. So these examples were chosen because they show that multiple failure modes may have the same response, which is that stage 2 loss of thrust. The initiating subsystem element is necessary because what causes one type of failure on a historical vehicle can cause a different failure on the subject vehicle. For instance, an engine failure may result in a loss of thrust response for a single engine stage, but it could result in a degraded plus thrust response on a multi-engine stage. So the next slide, I'll discuss more on failure response modes. Next slide, please. Okay, so failure response modes. A group of failure response modes that result in a homogeneous distribution of trajectory is a group of failure response modes that results in a failure response mode is a group of failure modes that result in a homogeneous distribution of trajectories prior to consideration of any mitigations or hazard control strategies. So while a failure mode contains the specifics on the initiating subsystem response and timing, the failure response mode is what's used to model the failure modes in your 450.119 method. The functional hazard analysis should define a failure mode to failure response mode relationship for the subject vehicle. And this is not an exhaustive list, but we provided a few examples of failure response modes. So for launch vehicles, that would be erratic flight, or fixed control, force offset, or malfunction turns. For reentry vehicles, that could be a tumbling ballistic trajectory due to attitude control failure, and a shallow trajectory maintaining attitude control due to deorbit overburn. Next slide, please. Okay, so the next few slides describe the data that the allocation must be consistent with. So the first part is the data available from all previous flights of vehicles developed and launched or re-entered in similar circumstances. So similarity criteria, as described previously, should be used to collect historical failure data to be used as the basis for the failure mode allocation. It's also noted that the similarity criteria here may be less restrictive than the criteria used for calculating the overall probability of failure or the biphase probability of failure due to limited failure data. What's most important is that the failure modes are reasonably foreseeable for the subject vehicle and phase event. So an example given here, turbo pump failure of a liquid propellant engine during stage 1 burn would be a credible failure mode for other liquid propellant engine burn stages, but it wouldn't apply to a solid propellant motor burn stage. Next slide, please. So the allocation must also be consistent with the data from previous flights of the vehicle stages or components developed and launched, re-entered, flown, or tested by the subject vehicle developer or operator. Such data may include previous experience involving similar vehicle, stage, or component design characteristics, development and integration processes, including the extent of integrated system testing, and level experience of the vehicle operation and development team members. So previous experience of the subject vehicle developer or operator should be accounted for when determining the probability of failure allocation, in addition to the flight outcomes of vehicles developed and launched or re-entered in similar circumstances. Previous experience may include past launches, re-entries, and tests, and that may include drop tests or glide flights. Tests may also be considered inapplicable or given less weight if the test environment was less severe, or if the intent was to test to fail, etc. And then similarity criteria, as described previously, again, may be considered here as applied to previous experience of the subject developer or operator for allocation purposes. So an example is if there's been significant staff turnover since the developer or operator's previous experience, and the new staff doesn't have a lot of experience with the new technology, then the previous experience may be weighed less when determining allocation. Next slide, please. Okay, so 450.131E describes the requirements for observed versus conditional failure rates. The probability of failure allocation must account for significant differences in the observed failure and the conditional failure rate. A probability of failure analysis must use a constant conditional failure rate for each phase of flight, unless there's clear and convincing evidence of a different conditional failure rate for a particular vehicle, stage, or phase of flight. So first, we define observed and conditional failure rates. The observed failure rate is the ratio of failures to attempts in a defined period of flight divided by the duration of the period. You'll also hear this called the unconditional failure rate or the absolute failure rate. The conditional failure rate is the probability per unit of time that a failure will occur at a given time, assuming success prior to that time. And we'll show some examples in the next couple slides. So what does it must account for significant differences means? This means that when calculating the observed failure rate, the likelihood of success in previous phases should be included in the calculation. Constant conditional failure rate is one that is uniformly distributed over time. This is a reasonable assumption to use unless there is clear and convincing evidence otherwise. So clear and convincing evidence otherwise is intended to mean informed by underlying knowledge of the subject vehicle or a stage or phase of flight of the subject vehicle. For example, for a reentry vehicle, heat flux and dynamic load functions compared to breakup thresholds may be used as a higher fidelity means of computing failure rate functions. Next slide, please. So the failure rate equations for a constant conditional failure rate and the observed failure rate are given here. The draft AC also has worked out examples for a simple two-stage vehicle, launch vehicle. Next slide, please. Again, the full worked example is in the draft AC, but you can see the results here, again, for a simple two-stage launch vehicle, assuming a constant conditional failure rate. The plot shows that the observed failure rate in the dotted line here is lower than the conditional failure rate. And that's because the probability of early flight failure makes it less probable that failures at later flight times will be observed. Next slide, please. So next we'll go over the application requirements for 45131. So the first application requirement is a description of the methods used in the probability of failure analysis in accordance with 115C. So a lot of that is what I've discussed already today. The probability of failure method should address each part of 131A through E, as well as each part of 450.115 C1 through 6. And I'll talk a little more about the 115 C1 through 6. Some resources are listed here as well. The AC 450.115-2 provides general guidance on documenting an FSA methodology. And then the draft AC for 131 provides a thoroughness checklist that an applicant can use to ensure that they have met each part of the requirement. Next slide, please. And then next, an applicant must submit a representative set of tabular data and graphs of the predicted failure rate and the cumulative failure probability for each foreseeable failure mode. So to break this down a little further, the tabular data should include the conditional failure rates by failure mode, the cumulative observed probability of failure by failure mode, and then the total observed probability of failure. The graph should include the observed failure rates by failure mode and the cumulative observed probability of failure by failure mode. And I'll show examples on the next slides. Also a note here, RAT's FTAR file or ABRDR's FTAR file format is acceptable for submitting this tabular data and graphs, since FAA has the software to display it. Next slide, please. So here is an example of the tables with an example format of what could be submitted to meet the requirement. The top table is conditional failure rate per failure mode. And then the bottom is the cumulative observed probability of failure by failure mode. And then you'll see there's a total cumulative probability of failure on the bottom row. Next slide, please. And then these are example accompanying graphs that show the data. Next slide, please. Okay, so as I mentioned before, the probability of failure methodology should address each part of 115 C1 through C6. Excuse me. Okay, sorry. Should address each part of C1 through C6. So For C1 and C2, I put some overall considerations on this slide. The method should begin with the scope of applicability, including what flights the method applies to, vehicle configurations, etc. Some other examples of what should be documented in the method include how the similar circumstances term is defined, how statistically valid is defined, descriptions of how data parameterization, data loading, and data selection is performed if using a database for the probability of failure calculations. Flight event phase and decomposition, including sequences and dependencies. Any conditional and observed probability of failure and failure rate calculations. What equations are used. How the failure is defined with respect to the subject vehicle, mishaps and anomalies, any allocation calculations, and how uncertainty is incorporated. The operator should clearly state assumptions, justifications, and logic used throughout the method. And this slide is not meant to be all-inclusive. Please refer to the thoroughness checklist included in the draft AC. Next slide, please. So 450.115c3 is the rationale for the level of fidelity. So the level of fidelity of the probability of failure method should be assessed, including the bias and uncertainty of the method. And this is described more again in the 115-2 AC that is available. The discussion on 115c3 should include sensitivity studies, such as the effects of different parameter selections to demonstrate performance of the model, and a sensitivity study that could include consequences of hypothetical failures. And then the level of fidelity discussion should consider both the overall method in addition to any allocation method used. Next slide, please. The evidence for validation and verification required by 450.101G is what's required by 115C4. As I keep mentioning, the 115-2 AC has more on this in general, but for probability of failure specifically, this should include a description of the review process, including the validation of historical flight data collection, any updates and accessibility. Basically, how does the operator confirm that the data used is valid? And then validation of the vehicle analysis for flight phases, flight events, phases, and failure modes. How does the operator confirm that all phases and failure modes are accounted for? And this section should also include any verification and validation evidence of software tools. And if only spreadsheets are used, then there should be evidence of validation of the formulas within the spreadsheet itself, rather than providing V&V of Excel program. Next slide, please. 115C5 describes the extent to which the benchmark conditions are comparable to foreseeable conditions of the intended operations. So benchmark conditions for the probability of failure analysis should include a comparison of how the method performs under different conditions, such as applied to flight history of other historical vehicles. And then there should also be a description of the check for validity of the method during the post-flight data review. So this is the checkpoint, such as using the example equation provided previously for method reevaluation that we talked about earlier. Next slide, please. I think we're almost to a question break. 115C6. This is the extent to which risk mitigations were accounted for in the analysis. So this really depends on the specific method, but some examples of probability of failure related risk mitigations are evidence for reliability of the vehicle's safety critical elements, and then any conservative choices in the probability of failure analysis itself, such as data selection, parameter selection, any uncertainty bounds, etc. Next slide, please. Okay, we will pause for questions.
Awesome. Thanks, Chrissy. So we do have one question to kick us off in the chat. How does a deorbiting upper stage attempt to initiate a reentry The reentry definition is limited to reentry vehicles, so an upper stage cannot perform a reentry.
Yeah, this is an odd thing in that this is actually it's in the reg this way. It's
Yeah.
not in the AC. The reg says upper stage initiate reentry. We've tried to answer that in the AC by really reading that as initiate a return, which is consistent with the definition for both reentry and disposal. So think of it as initiate a return rather than initiate a reentry. And we should
Right,
fix
and
the reg. Yeah.
And the
right, and
reason, sorry, go ahead, Chrissy.
I was just going to say, so we have in the AC that, this phrase was included in the reg to ensure that disposal is also included in previous flight, but agreed, it's written a little strangely.
And the reason it's not mimicking 113's language, the initiate a deorbit, the reason for that is because you wanted to pull in the scope of license before the deorbit attempt.
So why is the reg the way it is? And I would say we probably I don't know of a significance to why the reg is different in that way. Why it's not consistent with with the other part. I think it's an oversight in the reg that it reads the way that it does, as you've pointed out. A deorbiting upper stage cannot initiate a reentry. So I think that needs to get fixed. Exactly.
And for the
how
time
it's fixed,
being, replace reentry with return, and that's the interpretation.
yes. Yeah.
Okay.
Which is in 6.5 of the AC.
Okay, any other questions to ask during this time?
Yeah, so the way the AC is structured and the completion checklist is structured makes it seem like you perform your allocation analysis first and you apply your allocations, and then after you've applied your allocations, you perform the failure rate steps. Could you clarify if that is the correct order, or if you should be doing the failure rates first and then applying the allocations?
So I think the reg is not intended to provide the right sequence for an analysis. In fact, there's a whole lot of things where an operator will need to do things differently than the sequence that's in the reg. And I think it's really important to understand that that's the point of the reg, is not to say this is how the analysis should be performed. This is the requirements for what we're going to evaluate in an analysis. And those are very different things. I look at it, in general, safety needs to be done well before an application needs to get submitted. And all the safety analysis, certainly a lot of system safety, but even, preliminary FSA should get done way before the FAA is going to evaluate something. So these are how we look to see whether it's met everything. And, I think of 123, the population regulation is perhaps even more clear. It doesn't even approach trying to describe how one does that analysis. It's saying these are the things that need to get accounted for as you're doing this analysis. Have you done that? So that's especially for performance level regulation, we're not trying to prescribe this is the sequence in which an analysis gets done by any stretch. And I think that actually stifles innovation if we try to do that. We want to allow different ways of doing an analysis and that might be very much appropriate for vehicles that we haven't even thought of yet. I mean, I certainly know that with 417, one of the challenges with that was they really didn't even conceive of the type of vehicles that we have today. And so we're trying to be flexible and not just thinking about, well, how has analysis been done in the past, but be open to different ways of doing analysis in the future that might be quite different than what we think of now. While still meeting the core requirements of these are the things that are matter to this analysis.
Yeah, I definitely follow that and agree with that. Maybe I just point out then that I think that a C is using the phases of flight conditional probabilities in the rate equations, but that is not super clear. So maybe that can be clarified in the AC that the conditional probabilities that you're putting into the rate equations are the phases of flight probabilities, not the per failure mode probabilities in your examples.
I see. Right. Yes, when you have multiple failure modes interacting with each other, at the same parallel time, it does get how to account for that properly does get complicated, and I hope that we will be able to clarify that better in an MOC. So, and that's, I mean, our goal is eventually that the MOC will show a way of accomplishing the requirements, and like the MOC that's provided here, although it is simple. Coming up with an MOC is challenging work, as you guys who've done it know. And a new way of writing down and documenting a new way to do something is a significant exercise. So we're trying to show, okay, here for this case, this is a way that yes, you can go sequentially through it, and this MOC does meet all the requirements, and it is done in a sequential manner. But that's much more suitable to an MOC rather than specifying it as the way and requirements to accomplish it.
Yeah, understood. For the constant conditional rate equation, does the FAA have any limit on the conditional POF that should be used in that equation? In the MOC, you guys identified that it doesn't work for 100%, but it also starts to get pretty wacky as you get up closer to 100%. So is there a limit where we would say, hey, look, above this percentage, you need to do something else?
I don't have a specific, what I've been looking at, and I have written some draft stuff, is to think about this as with uncertainty and important. When you have a very high probability like that, then actually that's due to a lot of uncertainty, and you want to incorporate that uncertainty into your analysis rather than trying to do it as a specific mean. And that it actually can result in some situations where the sum of the absolute probabilities is greater than 1. That is another potential way to accomplish that. So,
yeah, I guess what my big concern is here is that if you're launching from the East Coast, most of your overflight comes at the end of the burn.
Exactly.
And
right.
When you use this equation, as your conditional POF starts going above 60%, the higher your conditional POF goes, the lower your overflight risk will get.
That is true, and that is part of why when we chose to put this example for 100% POF, defined it the way that we did, was to reasonably allocate it across the entire flight phase. So
I see. I was wondering if you were doing that because what you did in the example is you basically set the limit to a 50% conditional POF. The equations that you put in were basically saying, hey, don't let the exponential decay be any faster than what a 50% POF would have been. So is 50% like roughly where you guys think the limit is?
Yeah, I think that is a reasonable solution. Yes, you see what you're saying is the end probability is half of what the beginning one was.
Right. And
Yes.
don't let it, because if I put in 90%, my end probability will be 10 times less than my beginning.
Yeah.
Okay.
Yeah.
And then
And-
this is my last question for this, sorry. The statement about the Arctos FTAR files, are those being upgraded to handle constant conditional failure rates? Like the last time I used them, they could only do linear or constant observed. Like you couldn't put a constant conditional failure rate into them.
So I don't know about that. What we're saying is that file format isn't acceptable. It's just like Excel is an acceptable file format. That file format is acceptable. I also think there's a statement in the AC there where under certain conditions, approximating the constant conditional over linear can be is a close enough approximation.
Copy. Okay, yeah, I'm a little worried that the industry tools that we currently have available cannot process constant conditional failure rates, and so we may need to work on some steps for how to make that work.
Yeah, so the way that is implemented is it's implemented by breaking up a larger time frame into short enough time frames where a linear approximation is very close to an exponential decay.
Ah, okay. That makes
So
sense. That could be helpful to state
Yeah.
somewhere.
Yeah, and well, that's where we try to get at where we say, I'm pretty sure in the AC, I mean, I've been a while, but that's why we say specifically that a linear approximation can be acceptable under certain conditions, where I think it's like something like where the end is within 90% of what the beginning was or something like
Yeah,
that.
that's right.
So Simon, on both of these last couple of questions, if you if there can be comments too, that's very helpful for us to be able to see if we can work something better in. Really appreciate the feedback. I mean, these are very difficult documents to write, and once you look at them so many times, it's hard to know how a reader is actually going to understand them. So do appreciate that.
Yeah, definitely. I will send them as well.
All right, Christy, you ready to move forward?
Yep.
Okay, let's go.
Okay, so this is just an overall overview of the AC. Paragraph 6.1 through 6.8 go through exactly what I've just gone through today, 450.131A through F. There's expanded discussion, which we've touched on today, on similarity criteria, statistical validity, and then failure modes versus failure response modes. We do provide equations, including examples of the statistical validity of method checkpoint, and then observed and conditional failure rates. Paragraph 7.1 is a means of compliance for a simplified probability of failure analysis for reentry capsule. And as has been mentioned a couple times, the intent is to add additional means of compliance to this chapter 7 here, as they're available. And then paragraph 8 is a thoroughness checklist for the applicant to use when they're putting together a method. Next slide, please. Okay, so lastly, I'll go over the example MOC provided in the draft AC. This is the simplified probability of failure analysis for a reentry capsule. I'm just going to I'll say a high-level overview. Not going to go through every single calculation, but those are in the draft AC. So the purpose of this example AC is a simplified conservative probability of failure analysis for a class of reentry capsules described below. So the scope of this MOC applies to flights of reentry capsules with the following characteristics. Reentry is from low Earth orbit to Earth's atmosphere. The vehicle consists of the support bus and a capsule that separate before entry into the atmosphere. And the capsule has a parachute, but no aero control services or reaction control system. So just to note here, the applicant may adopt this method with modifications subject to FAA approval. So If an operator's vehicle is slightly outside of scope, but they still think this method mostly applies, they can, again, apply modifications subject to FAA approval. Next slide, please. So step one, starting with a nominal trajectory, identify milestones and divide the reentry into the flight phases. And the flight phases must cover the scope of the FSA per 450.113A4. So the milestones for the reentry capsule are listed here: deorbit burn start, deorbit burn end, capsule bus separation, entry interface, start of main engine heating, end of main heating, parachute deployment, and touchdown. And from there, flight phases are defined using those milestones with a start and end to each flight phase, clearly defined start and end to each flight phase. So when an applicant uses the MOC directly and their vehicle falls within the scope, they can use these flight phases as defined here. And next slide, please. So step two is to identify the reasonably foreseeable failure response modes per flight phase. And so those failure response modes are listed here. They include random reentry, incorrect start state vector, ballistic tumble, underburn, overburn, explosion, and uncontrolled intact fall, aerodynamics error, aerothermal and aerodynamic breakup, ballistic fall, and partial parachute. So again, same thing as before. If your reentry vehicle falls within the scope of applicability and you wish to use this MOC, you can use these failure response modes directly. Next slide, please. And then the MOC then maps these failure response modes to the applicable phases of flight as shown here. Next slide, please. So step three, you would assume a conditional probability of failure of 1 per failure response mode per phase. And from there, you can compute the conditional failure rate per failure response mode per phase, and then the observed failure rate and the cumulative probabilities of failure. And the FAA has provided equations that they have determined is reasonable to use if applying this MOC. So I won't read these equations here, but we provide the equations in the draft AC for conditional failure rate and observed failure rate with the GNC parameters as listed here. Next slide, please. And then the observed failure rate is provided here. Next slide, please. Step 4 is to create a representative set of tabular data and graphs as required by 450.131 F2. So a note here, the cumulative failure probability per phase is equal to the number of failure response modes, and that's because the cumulative failure probability is equal to 1 per failure response mode per phase. So you go through steps 1 through 4 for the nominal trajectory itself, and then you would repeat those steps, or you would repeat steps 1 through 3 for each of the variability trajectories. We wouldn't require the tabular data and graphs for each variability trajectory. Next slide, please. So then an example is provided here, given a reentry timeline as shown. So the applicant would insert their own reentry timeline and come up with flight phases by time as shown here. Next slide, please. And then the applicant would calculate this table using their specific flight timeline to calculate the C parameter, and then in turn the cumulative probability of failure per phase, which ends up being the number of failure modes per phase, and then the total cumulative probability of failure. Next slide, please. And then here are examples of the plots that would be provided if you were to use the example MOC. The left shows the observed failure rates, and then the right shows the cumulative probability of failure summed across all phases and failure response modes. Next slide, please. And that is all I have. I think I saw some questions in the chat.
Yep, just a few more questions. So first question, where would the key flight safety events be addressed in this means of compliance? Should they be included in step one, or is it something addressed separately?
So if you're using this MOC, you can use those flight phases directly. Does that answer the question?
Saying that FAA has established that separately those flight phases meet the criteria for not having more than one key flight safety event, and we don't have to provide anything else to verify that.
For the probability of failure analysis, correct. Yeah. I think you would still, I'm not sure what the other requirements are that require the key flight safety events off the top of my head. I think you would still have to provide those.
Okay.
Yeah, so I think 45108 mentions key flight safety events, so you would still need to identify those. Well, that's for end of flight abort. But yeah, I guess for the probability of failure requirements itself, then correct. Yeah, you would not need to go through and identify the key flight safety events.
Okay. Can you walk through the logic for why random reentry is not included as a deorbit ignition failure response mode?
That may be a good comment to submit for disposition, unless anyone has any initial thoughts on that.
Yeah, I was wondering if it was because if you just fail to ignite, that re-entry vehicle is still potentially healthy on orbit, still could re-enter at a later time. And so, it's kind of like the equivalent of a launch vehicle that just aborted the countdown. But I wanted to see if that was your thinking. I will send it, and then if that wasn't your thinking, you can give me the alternative.
Yeah, thanks. If you can send that, we'll probably try to add a footnote. I think your answer is correct there. So, but would want to go back to our notes.
All right. Let's see. Why are the failure causes for an overburn or an underburn each considered when the failure response is the same?
So in this case, I think that it's not necessarily always the same for every vehicle. There may be different mitigations that are in place for those cases that we've seen. So it's conservative to capture them separately. This is a great example where you potentially could tailor this MOC for your vehicle if it matters to be different.
Okay. Simon, did we address the question that you put in the chat? I feel like we talked about that.
Not yet. I was just curious because in the AC, the example that you showed in the slides gave the probabilities by failure mode, and then in the MOC, the
Okay.
failures are given by phase. So I was wondering which one it is.
So the MOC has failure probabilities by phase and by mode. It's just because of how this MOC works out for each mode, all the modes have identical failure probabilities within each phase.
No, I followed that, but wouldn't the plot, the graph for 131 F2 be split up by failure modes and then track how those cumulative probabilities grow per failure mode like
No.
it is in figure 4?
Interesting question.
Do you, sorry,
Yeah.
do you mean for the, are you talking about the figure in the means of compliance?
Yeah, so
Yeah.
figure 6 in the means of compliance is fairly different from what presented in figure 4 in the
Yeah,
AC.
I think, can you submit that as a comment? I understand. I think looking back at the reg, we may have gotten that one incorrected. It really should have done like that, your response mode.
Yep,
Well,
I will.
The per failure response mode, they would all look the same, but maybe
They
I'm
would
not
look
understanding.
they would look different because different failure response modes show up in different phases. So
Yeah.
like
Yes,
your
okay,
ballistic tumble is going to
okay,
end up much higher than
Yep.
your random reentry.
got it.
Thank you.
All right. So expanding on a previous question related to design iterations of the same vehicle, can AST provide further definition of the term class in the context of a class of vehicles? Can an applicant define its own class of vehicles where future productions are not considered new, but instead part of the applicant's definition of a class of vehicles? Reading the AC, the term class is limited to reentry vehicle characteristics.
So, I mean, this all comes down to whether, I mean, I think, what is a new vehicle and what is a derivative of an existing one? And that is, I mean, all I can say is that is definitely a gray situation. There's, I mean, there's no, and we see this in every other field too, is when is something really new? How do you decide for software when are you, this is a minor version or a major version? It's a sense, it's very hard to draw a line in the sand there. So I think that's a difficult thing to identify as a general principle. It's easy to say on the ends, but in that middle area, it is very it's squishy. Make a good argument for why it is still the same vehicle because the design similarity is high enough, then that would be, but it really comes down to how similar is the design. And generally, you probably, it's safer to be more conservative, whichever answer that is. So, if you're accounting for uncertainty, say 115B, then there is some amount of uncertainty there. So look at which is a more conservative approach.
Right, and that's kind of why I use the term, use the phrasing where we're able to propose that to AST and say we are proposing this class of vehicles. I wouldn't say this is going to be applicable to everyone, but within the context of this application, we are defining the class of vehicles of this type and these characteristics, and AST is capable of granting that.
So I think there's a difference here. An MOC can apply to a class of vehicles because they're of a vehicle type, but that's an MOC can apply. That doesn't mean that results are that it's not a new vehicle. An MOC can apply to multiple different kinds of new vehicle. Multiple different new vehicles. That's that. I mean, like, for example, this MOC that is here would apply to any reentry capsule that is, meets the scope criteria. They could all apply to, they could all be new vehicles, but they're all of that. The class is defined by the scope that's listed in section 7.12.
I see the distinction there. Thanks.
Right. Another question. For discrete flight events such as payload separation for a launch vehicle, how long is the duration for the probability of failure calculation purposes? In real flight, the events are instantaneous. For example, if a payload fairing separation occurs at 100 seconds according to the mission timeline, should the operator set the payload failure the payload fairing time, the discrete time, to be between 99 and 101 seconds. So essentially, what duration should you use for discrete events in your probability of failure calculation?
This is actually more of a question for sampling in terms of your malfunction trajectory analysis and your debris dispersion. So the probability of failure analysis it can end with that. Now, I would say there's uncertainty in when these events occur. There's also the payload. I mean, a separation event, although there is a moment when vehicles are no longer in contact. The event itself is very short duration, but not truly instantaneous. Real world events are, that process of separation takes time. So in general, most of the time, we often have used 1 second as a reasonable interval. I have seen cases with highly dynamic vehicles where that's not sufficient, but for most orbital launch vehicles, given their acceleration profile, 1 second works, but can't say that's necessarily always true.
Yeah, what we have in the AC, for discrete events, the observed failure probability should be allocated to the state at which the event occurs in each 117 normal trajectory simulation. So I think it's what Eric said, but yeah, I think 1 second has been pretty standard.
All right. So the next question, the last question I have written down, I believe it's referencing the example in the AC. How was an observed failure rate of 30% derived when there have been only 3 capsule reentry failures and over 300 landings? Actually, three reentry vehicles, including STS.
So the example means of compliance, it's supposed to be it's a very conservative way of doing it and applying a probability of failure of 1 for each phase of flight and for each failure mode. So it is conservative, but it's a simple method that an applicant can use such that they don't have to base their probability of failure on historical data, if that makes sense.
Why would a capsule reentry operator not want to base it on previous capsule reentry since it has such a good record?
The short answer, that some capsules, the hazard, even if it fails, is very small, and it makes the analysis very easy to justify. You can live with it when you're doing, for a small capsule landing remotely. This just makes it a real simple way to approach things.
Yeah,
Easy to demonstrate compliance with CEC and other things too. Oh, go ahead, Sean.
Yeah, if you can show the analysis closes with that very conservative assumption, and you can live with the resulting mitigations from a program level, that can also be justification to reduce some of the system safety level of rigor for 450.143 and 450.141. Basically, what you're saying is this vehicle could fail in any way I can predict, and that's accounted for in the risk analysis, and I still meet the criteria. So you can make an argument to reduce the level of rigor in the system safety requirements.
Thank you.
Okay. All right. Well, we're about 10 minutes to our time. I've exhausted the questions in the chat. Any final questions before we close today? Chrissy, we've got through all the slides, correct?
Yes.
Yes. Any final questions before we close?
If there's no one else, I did miss one. If we could go back to the exhibits the potential slide. The language in here and in the AC was saying, when you're trying to figure out if something exhibits the potential, assess if it likely would have caused a failure on another mission. And I wanted to get the FAA's opinion on how much weight operators should put behind that language, because likely would have caused a failure is a bit of a higher bar than I think we have historically seen be applied to the exhibits the potential language. Previously, I would say the bar that has been applied is, could it possibly have caused a failure? And if it could have possibly caused a failure, then it meets the exhibits the potential. But in the AC, you're saying it needs to likely cause a failure. So yeah, I wanted to see if you had thoughts on that.
Which slide was that, Chrissy?
Sorry, it was in
It's in B, so it's probably forward.
halfway through, yeah.
There it is.
Got it.
I think that might be one more forward. I did see the language in the slides.
Yeah, no, that was it. It was on the previous slide, in the middle of the page.
Yeah, but this one doesn't have the like. Can you go to the next slide?
Yeah,
Sorry.
Yeah. Can you submit a comment on that one? I understand what you're saying, and
Okay, yeah.
yes, submit a comment on that one. I think so. I look back at the actual AC text too. It's section 6.44.
Yeah, we acknowledge this is a gray area. We tried to provide some specific examples in here, but yeah, additional comments would be helpful for us to consider, I think.
All right. I'm not hearing any other questions. I don't see any other questions in the chat. I want to thank everybody for their time today. Thank you, Chrissy, for taking us through these POF workshop slides, and Dr. Larson for all of your assistance and the questions. And with that, I think we can close for today. Thank you.
Thank you, everyone.